Yeah, this is going to be debugging and exploring Clojure applications with FlowStorm. And yeah, so a little bit about my journey to Clojure. This is the slide that I was saying I have here. So I've been writing software since the 90s, started with C, C++, and Java until I found Common Lisp around 2004. And started doing all my hobby projects there while still working in Java. Found Clojure around 2011 and started working almost full-time and currently full-time since that date. I also do some web stuff and I use Clojure script whenever I can. So yeah, this is going to be the agenda for today. I will talk a little bit about debuggers and Clojure in general. Then tracing debuggers in particular. Then I have a live demo where I'm going to try to use FlowStorm to debug some pieces of code there, some examples, so I can demo its features. Then I will talk a little bit about FlowStorm internals, how it works inside, how you can build something like this if you're interested. Some known limitations that these techniques have currently, and then a section for questions at the end. So yeah, before starting with debuggers and Clojures, I think there is an interesting question. I mean, Clojure has the REPL. Does it need a debugger? There are blog posts like this one, REPL debugging no stack trace required by Stuart Holloway, where he talked about that having the REPL, he goes about debugging a piece of code, a piece of Clojure code, by even disable the stack trace and Clojure error messages by just using the REPL. And the REPL and the editor REPL connection. So the strategy there, we are going to see an example, but the strategy there is blindly subdivide the problem. So use def to define globally your local scope, and then using eval from editor, you can eval every subform and try to figure out what's happening. It's that mix and match, execute the code in your head while doing this. So to be more clear, this is what he proposes, and I think it's an amazing technique. It's very powerful. So if you have this function here that is you want to try to understand its parts, what it says is, okay, you have a local environment here of n, which is a parameter. You can define it globally, and then you can grab pieces of your code and evaluate them. So you can say, okay, this goes into 44, and this it's false or whatever. And it's an amazing technique that not a lot of language have. So yeah, this technique, it's nice, but I think it has a couple of problems. First, def isn't always easy to use. This is a very small example, and in this case, n, the input parameter, it's just a number. But on most applications I've worked, your environment or your parameters or whatever are very complex structure, nested maps with vectors and a lot of stuff. So it's not easy to go and type there. Even with libraries like scope capture, even when you try to put some code that it's just capture all your scope, so you can then go and apply that technique, it doesn't always work, because if you have loops, recursions, reducing functions, maps, filter, whatever that executes multiple times inside the same frame, then you're only capturing the last iteration. So I didn't found that technique particularly useful in a lot of situations. And also for this thing of executing the code in your head, Clojure is not super easy on that regard, because we have nil panning. So sometimes finding where nils are coming from, it's not super straightforward. And also Clojure is a dynamically typed language. So it's hard to reason without seeing shapes of things. The classical function that receives a user as an input and you have no idea what a user is. I mean, by just reading the code, could be a map, could be anything. So I think even that I think this strategy is amazing to have it, I think a debugger can improve further that already amazing REPL debugging thing. Also, I think the Clojure community has been working on a bunch of tools to aid the debugging process. So yeah, I think that there is room for debuggers. So how can we debug something, or the ways I know to debug something, to write a debugger for Clojure on the JVM? There are two paths that I'm aware of. One is going the Java debugging interface or directly to the Java tooling interface, which is what most Java debuggers like Eclipse or IntelliJ or whatever are using. You can directly connect into the internals of the JVM, and you can stop the JVM execution, watch around your memory, fields, the value of fields for some instances or whatever. And the other way I know about it's instrument by code rewriting. This has nothing to do with the JVM in particular. This is, we grab a Clojure form we want to debug, and we rewrite it. We rewrite it automatically rewrite it in a way that it does exactly the same that it's supposed to do, but we also add code so we can block or trace or whatever we are interested in. So that's code transformation. We're going to see some example of each of those. So for the first one, for going the Java debugging interface route, the only example in Clojure I know about is cursive. I'm not 100% sure since the code isn't public, but yeah, it's using the IntelliJ infrastructure, and it's connecting directly to the Java debugging interface probably. It has some pros. So it's instrumenting at the JVM level, and which is super efficient and can work with Java also. But it has some cons. Everything around JVM debugging is line and place oriented. Even the debugging information inside class files that only support lines. And this it's kind of a problem for Clojure, because Clojure is expression oriented, not line oriented. So a lot of time we have multiple expressions in one line. And also Clojure is not place oriented. So everything on the Java debugging interface is around, okay, stop the VM that I want to look around from memory locations, which makes sense because on mutable languages, the only way you can do some debugging is to stop the world, to look around and then continue execution. The other way, that this instrument by code rewriting, we have examples. For example, the Cider debugger is doing this, the Calva debugger is doing that, because it's using, I think, as Cider and REPL. FlowStorm does this, debugs, and probably more debuggers use the same technique. The pros of this technique are we get nice expression debugging, not line-based one. We can implement tracing debuggers or blocking debuggers, both of them. With the Java debugging interface, you can, as far as I know, you can just put a breakpoint and stop everything. It's Clojure aware because we are rewriting, and we have some cons. Of course, it's not as efficient. When we instrument, we are adding a bunch of code, so yeah, when you run it, it's going to run slower. It's going to consume more memory. And okay, let's, since most languages have like blocking debuggers, which is steppers and all that stuff. Let's talk a little bit about tracing debuggers first. So tracing debuggers are basically, you instrument somehow the code for tracing, then you run that code, and you never put back breakpoints or anything. You just run the thing, collect all the traces, and then you need to have some kind of tool that lets you visualize what happened with that execution. So your thing ran, and now you want to see what happened for debugging or understanding. It has some pros. First, you get time travel because you have the traces for the entire execution since the beginning to the end and everything in between. You can jump into at the beginning of the execution, the end, and wander around. And also you have multiple visualizations. So single stepping, it's one of the tools you can use to walk over those traces. But as we are going to see with FlowStorm, we have more visualizations. And the cons is it's resource intensive. If we blindly trace everything and the application has a lot of hot loops or whatever, it's going to consume more memory and also be slower. Other examples of this kind of tracing debuggers are the RR project, which is a low-level tracing debugger for C, C++, Rust, and some native languages. It's normally, I think, implemented in two parts. So one part is instrumentation and tracing. Then the other part is, okay, I'm collecting a bunch of traces and I want to visualize, analyze that somehow. This can be done under the same process, both things under the same process, or in remote process, even on different machines. So you can instrument something on some machine, which trace through a socket or whatever, and then you can capture all those traces on the other side and yeah, apply some analysis tools. So what happens when FlowStorm instrument a piece of code? It will trace function calls, functions returns, bounded values, for example, for let bindings, loop bindings, or function arguments, all that stuff. And also all expression return values. So all intermediate expressions will be traced. A couple of questions I find interesting. Here is, isn't tracing everything super expensive? And one answer here is, what FlowStorm is doing is don't serialize, just retain pointers and snapshot reference. What this means is like tracing doesn't mean grab every value and serialize it, like when you apply a print line, which is basically serialized to string every value you are interested in. This is just retain the pointer so the garbage collector doesn't collect it. And if you are tracing a mutable thing, for example, a reference, take a snapshot, the reference, and just grab that pointer. So traces are just pointer retention, nothing more than that. And another valid question, I think, is why aren't tracing debuggers common in other languages? I mean, most language has these blocking debuggers. And I think, and that's my opinion, that Clojure is pretty special in this respect because of immutability. You can just retain pointers, and Clojure is also expression-based, not statement-based, which makes things easier. And it's also Clojure, it's easy to instrument because Clojure is built, the entire language is, if you get rid of macros, it's built on top of some small amount of primitives. So instrumenting Clojure code is much easier, I think, than other languages. So, okay, that was for tracing debuggers. Now, FlowStorm, an overview of FlowStorm. It's a Clojure and Clojure script debugger. It instruments code by rewriting, so it doesn't connect to the Java debugging interface or anything like that. It's a tracing debugger. It's meant for development, not production. it's designed to improve the REPL debugging experience. So it's not like debugging with the REPL or with the FlowStorm. It can work together to enhance that experience. And it's also IDE independent. It can be integrated, but you don't need any special IDE to use FlowStorm. So whatever it works for you. So, okay, I will start now with the live demo. I will move these slides aside and start the debugger. So for running the debugger, you need one thing, just to, okay, before that, one thing is that these slides you are seeing here are bucket by a REPL. So there is a Clojure process running there, a JVM. I will execute code from the slides. So what you need to start the debugger is just call this function. And it's called local connect, because Flowstone can run in two different ways. One is starting the debugger under the same JVM process that your application is running. And the other one is called remote connect. When you want to start the debugger in one process, possibly in a different machine, and then you have your application process and you want to connect both remotely through sockets. So yeah. So here's the empty debugger just started, and let's try to debug some code with it. So this is some random Clojure code, which just have some numbers. We filter them, partition them, do mapping, dropping, and we want to sum all those numbers in the end. The first thing it's new here, it's this arc trace. So now our process is connected to the debugger. Whenever we want to debug a piece of code, we write arc trace on top of it if we want to instrument it plus run it. So that is going to do both things. So let's run it and see what happened. So first thing there is a null pointer exception. So we are going to ignore the error and the traces and see how we can use the debugger to try to figure out what is wrong with this piece of code. So coming here into the debugger, a couple of things happen. A flow has been created with and code has run under the thread 17 in this case. And we see the source code here and a couple of tools to step over the source code. So we can start clicking next, and we start stepping over the evaluation. One interesting thing already, it's that, yeah, the first thing that gets evaluated when we were running this piece of code, it's not range of 70. It's start like evaluating the plus variable, it's evaluating into the core plus function, and so on. So that's interesting, because most of the time you think, okay, this is the first thing that is running. But yeah, so we can use next and back to move around in time. For each expression, we're going to see the value printed there. We can explore this. But before jumping around, we can, when we executed this, it raises an exception. One nice trick we can use to immediately go into the exception, or pretty near into exception code, is go to the last trace. This is going to move the debugger to the last thing it was able to capture. So right before the exception. So it is jumping automatically to the drop expression here. So right before the plus. So if you look at what that drop evaluated into, there is a suspicious nil value here. And the next expression to run is a reduce with a plus, and of course that's going to raise an exception of nil. But yeah, now we figure out, okay, there is a nil here. Why is this nil happening? We can start stepping back. Okay, map second, the nil is still there. We go one back, partition all, it's creating partitions, and it looks like every partition has two numbers, but the last one have only one. So it's pretty easy to figure out, okay, there's something wrong with this piece of code. this second is always going to give nil on partition that has size 1. So yeah, that is how you can use it to move around and try to understand a piece of code. I also think that this stuff is good for teaching and learning, because when you're trying to explain Clojure, it's nice to have something. So instead of asking the person to imagine all this stuff, you can click around and show them what is the flow of a Clojure execution. So, okay, let's close this and move to the next example. This is the example I was talking about from the Stuart Holloway blog post. It's just whatever function here. And the new thing here is that now it's saying trace here and not rtrace. So the difference is tracing, it's for just instrumenting things, not running anything, because for functions, multi-methods, typed extensions or whatever, you're not running the thing. You just want to, okay, instrument the thing. Something else is going to run it. And yeah, so let's evaluate that function. So that function is now traced. And let's see what it takes to find a bug like that with this debugger. So we run the function, we see there is an exception, so something went wrong. We are not even going to read the error message of or the stack trace. And we are going to come to the debugger here. Because the code is short, the debugger is putting everything in one line. But so again, we just keep one click, go to last thing, and the last thing that executes is n, who evaluated to 24, and we are going to try to do a first of n. So that's a problem. We cannot do first words on sequences. We are trying to do first on this. But yeah, then you can also click around to see other code. So yeah, I find that pretty powerful. Also, there is one other new thing here, is that there is a funnel here on this tab instead of flow ID 0 like in the previous example. I'm going to try to explain this on the next slide. So when you trace a function like this sum function that doesn't do anything, if you trace that, you can call that function, that traces functions in two ways. One is simply call the function, and the other is rtracing that function, which is instrument and execute. So you can think of rtrace like doing this, which is dynamically binding flow ID 0 and then instrument and running the thing. So everything that happened before is going to go into some flow ID 0. When you just call the thing, a lot of traces are going to be generated here, but because they don't belong to any specific flow, they are catched by that funnel. They are like orphan traces. They are going to be catched by this funnel flow. This flow thing is like, because you can run multiple flows and then be able to compare them in the debugger, but yeah. So, okay, another example, it's library. So far we have been instrumenting code that we have there in our buffers. It's probably our code, but what about libraries? So the example here is going to be, let's require base64 encoder, the Clojure one. And let's try to run this little example, which is grab all the bytes of London Clojure meetup and base64 encode them. Okay, and it's that stuff. Now, let's say we want to debug or understand how that encode is working. So one thing we can do to instrument that is to use the browser. The browser is this tool here that it's going to show a lot of all the namespaces that are currently loaded. When we click them, we see all the bars inside the namespace. And when we click on the bar, we are going to see documentation, arguments. I mean, this is just for exploring, but we also have the ability to instrument any function we want from here. So to instrument this, we are going to search here for base 64 something, okay? Here is the namespace of the library. We can try to instrument each of these, or we can just go and click instrument this namespace entirely, okay? And this has instrument the entire thing. So let's see what happened when we run the code again. Okay, now we can see this encode function here on the debugger, and we can start stepping over the code. It is going to call other functions. We can keep clicking. It's because we instrumented the entire namespace, we can just walk around, click around, and try to figure out everything. Here we have all the locals that are for this specific point in time. And here is the current evaluation. I'm going to try to demo another feature here because we have a loop here. So as you can see, every time I click on something, the debugger just goes there immediately and shows me what's the value of that expression I just clicked. But what happens when we have like loops, where, for example, this I here for this function frame probably executed multiple times, one for each iteration or whatever. So when I click there, instead of jumping, it's going to open this menu where it's going to show me, okay, these are all the values that I took inside this frame. So I can click any of those. For example, if I want to go to the last iteration of this loop, I would probably click on this one. And that just moved the debugger to that point in time. So now I can start stepping or whatever, but only inside that iteration. So this is nice because trying to step over something that has a loop of 1,000,000, it's crazy. I mean, so yeah, this is another tool for moving, for jumping around through time. Okay, so let's close this. Let's move to another example. Multi-threading support. So here we are going to grab the range of 5, and we are going to do a parallel map. So all this is going to execute in parallel, bucket by a thread pool. So let's see what happens when we run this. Okay, as you can see here, a bunch of threads are working. The first one, it's only showing code for the outer thing. Okay, and if you click on the executions, it's only going to move over the outer stuff. But then these threads are probably executing only these parts. Okay, and why do we have, I mean, the range has 5 and we have like less traces. And this is because it is backed by a thread pool. So some threads are going to take more than one of these. We can check that, for example, if we want. I haven't shown you this tool yet, but for example, this thread got the calls for square 0 and square 1. This other one got the call for 1 and 3. And this other thread is working with the square of 2. But yeah, we can use this for debugging multi-threading applications also. Slack. Okay. Let's move on to a different example. This is now kind of the same, but here we are going to try to instrument an entire code base. This line here is just calling the Clojure script compiler, telling it compile this file and then compile it for the target of Node.js and then execute it under Node.js. So that's what this line do. If you want to look at the file we are compiling, is this simple file. We have just a factorial, recursive factorial function, and then console log that is saying, okay, factorial of 5 is whatever. Okay, so let's run this, and then that is compiling and running it. It should be done in a minute. Okay, and if we go to the REPL now, we are going to see here factorial of 5 is 120, so everything's fine. Now, what if we want to like instrument the entire Clojure script compiler to debug, because we found there is an error where the compiler is doing something wrong when we, for this specific piece of Clojure script, or we simply want to understand how it works. So again, we go to the browser here, we do CLJS, whatever, we grab a lot of CLJS namespaces, and here we are going to instrument the entire thing. So I will use this example to also talk about these two things here. As you can see, we have like instrument the namespaces light or full. What is this about? So when you want to instrument a very big code base, you're not probably interested in absolutely everything. You want to probably first start with only like the function calls and function returns, and then you can instrument everything into some specific functions you are interested about. So yeah, instrumenting like this, it's going to instrument all those namespaces, but only for function calls and function return. You can see here that it's instrumenting. Okay, it's done. And let's see what happens if we run it. I'm going to run it with rtrace. So everything goes into flow 80. Let's run it. We can already see a debugger there. Let's wait for the compilation and running to be done. It's going to be a little slower because it's instrumented. And if we jump here, we see a lot of instrumentation logging. But again, factorial of 5 is 120. So that's important because it says that the instrumentation didn't broke the compiler or anything. Remember, we are rewriting code. Yeah, now we have this flow here. Some traces got into the funnel trace, but we are going to ignore this for now. Let's focus on the main thing. So this is the code we just made. So we are not going to step over the entire compilation because it's like single stepping over the entire compiler is crazy. So I'm going to demo a different tools, different ways of approaching from a high level view, some executions. So the next tool, we have been working with this tool, the code tool. The next one is called the call stack tree, which is a tree of all the functions that executed there. We can expand. So yeah, main function call it normalize, and this other normalize on a different namespace and so on. We can click around here and to check the arguments vector and the return value of that function. Okay, so by clicking around, we can see those. Sometimes I find useful that, okay, this for the compiler, this tree is probably super big, and we want to be able to search around. For example, I know I'm compiling a file that is compiling something called factorial, for example. Can we find in this tree something that has something to do with factorial? Okay, so this search function here is going to search over functions names and string serializations of its arguments. So if I run this, it's going to search for something that contains factorial. It found something here. You can click here to help you locate the thing. So there is an evaluate form here, And if you look at the arguments, it's probably going to say factorial somewhere. So one of the arguments is the form we are trying to compile. So it looks like we found something about our forms there. Another feature is if we want to jump, for example, we are interested in stepping over this piece of code or any other, we can right click here and say go to trace. And this is going to jump immediately to that, so we can step over that piece of code if you are interested in that. We are going to do it a bit later. Another feature, it's a REPL integration. So we are looking at some, not that one here. We are looking at some values here. Whenever this is called the value inspector. We have a value inspector here for the arguments, one here for the return values. If we use the code stepping tool, we are going to have one value here for the current value we are looking at. So in every of these value inspector, we can do def, and it's going to ask us for a var name. Let's say it's going to be args. And what that's going to do is going to define in the REPL. Let's go to the REPL. And now under args, we have the value here. So whatever value we see here, we can give it a name and then use it for the REPL. So, I mean, I don't know, count of args or whatever. So we can work from the REPL with that value. We can do the same for this thing. This is a return, so we are going to put R, and now we have R here, and we can work with the return string, which is the JavaScript compilation of our factorial function. Yeah, so back to slides. This is the call stack tree, but there is another tool that helps us having looking at the execution for a high-level view, which is the functions list. So these are all the functions that has been called for that compilation, sorted by the amount of time they had been called. Okay, so for compiling that, there are a lot of functions involved. There is some coloring here. So black ones are just normal function. Magenta ones are multi-method calls. And then we also have some green ones, which are protocols or interface implementations. So yeah, let's say we are interested in parsing or whatever on the ClojureScript compiler. Yeah, here we can see, for example, a multi-method that's called, it's parse. The dispatch value is the namespace form. So it looks like this is parsing the namespaces forms. Here it's parsing lets, parsing sets, whatever. So if we want to look at all the function calls, because there are 85 function calls for this function, we can double click it and it's going to show them here. Each of these is the vector with all the arguments. Sometimes we are not interested in every argument because some of them are just noise for what we are trying to figure out. So we can remove some of them. Let's only let argument number 3, and let's update this. So now let's look better. These are all the calls of parse with different namespaces forms. So yeah, let's say we are interested in this one, which is like it's parsing our namespace. So again, we can say go to exactly this moment in the debugger. So now we have the code for this def method parse, but exactly when it's going to parse our form. If you remember, we instrumented everything with light, so we don't have all the things that happened here. But now we are interested in this function. We can right click and say, okay, I want to fully instrument this form. Okay. Now this is also instrument. We need to rerun the compilation so we can capture this part of the thing. So we have this button here, which is basically rerun the flow. We click it, and it's rerunning it. If we go to the REPL, we will have here, okay, factorial of 5 is 120. So yeah, it's already finished. And now let's go back to that position, which was parse. Let's remove some of these so it's easy to find. And we instrumented this parse namespace. We were trying to understand this compilation. So now we have the full instrumentation. So we can step over the thing, try to understand what the compiler is doing. Okay, have some segments and whatnot. This looks interesting, whatever. We can say, okay, interesting. And now we have it here to keep working from the REPL. So yeah, we can use all this stuff to try to understand some execution, try to find some bug, or sometimes just to understand a code base when you don't know about it. So the first time you see it, it's nice to instrument everything, run something, and then try to understand the code base by looking at the execution. Okay. So let's close this. We don't need it anymore. And this is going to be the last example, which is conditional tracing. So for demoing this, I created a small animation here in Clojure, a small game. Imagine that this is a game. And this is, so the game loop, it's calling 60 times per second update the state, which is calling update ball state. This is just handling the bouncing, like wall bouncing of the ball. So if we are interested in debugging this piece of code, adding a trace here, it's not a good thing to do, because remember that this is being called 60 times per second. So it's going to generate a lot of traces, it's going to consume a lot of memory, and we're probably not interested in all the situations, like because they are going to be almost the same. So what you can do in those cases is conditional tracing. So the only thing we have changed it here, it's basically the important part is ctrace, which is, it means conditional trace. It's exactly like trace. So you put it before something and it's going to instrument that. The only difference is that it's going to disable traces by default. So everything is instrumented, but it's not tracing anything. But we have a way of enabling and disabling traces on things, only on things we are interested in. For example, here, adding this metadata on top of this form, we are saying, okay, enable traces when X of the ball is less or equal to 0. So whenever the ball is hitting this wall. I'm not interested in everything else because I know, I don't know, it's an example. So let's instrument that. And for the other function, we can trace it completely, because it doesn't matter that everything is instrumented, because this function, which is on top of this one, is going to control when traces are evaluated or when traces are enabled or disabled. So yeah, we can also track that. Now, if we go to this tree here and keep updating it, as you're going to see, only it's going to generate traces when the ball is hitting the left wall. So it's not a lot of traces. And if we are interested in, okay, let's see what happened here, we can jump there, step over the code and try to figure out what happened, all the same tools as before. But as you can see here on the counters, we are still collecting traces, but not a great amount of traces, because we are only conditional tracing. Okay, so yeah, let's stop the game and close this one. So that was conditional tracing, and that's the end of the live demo. Now I want to talk a little bit about FlowStorm internals. I mean, how it's done, how you can create something like this if you're interested in internals. So a high-level overview of instrumentation in particular, it's this thing here. So we grab a form, any Clojure form, then we tag the form recursively. What does this mean is we walk the form tree and we add metadata to every node of the tree with the coordinate. So this is, we are going to put coordinates on the tree. So when we macro expand them, so we need to macro expand the thing to get rid of all the macros. When we macro expand it, we will still have the coordinates because macro expansion is going to change all the coordinates, and it's and then we need to, when that code executes, we need to refer to the original coordinate. This trick I got from the Cider debugger. It's pretty interesting. Once we have tagged the code with coordinates and macro expanded everything, now we can instrument it recursively. Instrument means walk that code and add tracing instruction or blocking instructions or whatever. But this is much easier now because after macro expansions, you only need to, your visitor only needs to work with Clojure primitives, which aren't that much. Okay, so this is an example of instrumentation. Let's say we are instrumenting this little function here, which is foo of A and B, and C is A plus B, and we are returning C multiplied by 2. So when you trace it, this is the code that we are generating, which is code that is going to do exactly the same, but everything that's in yellow here are traces that we are adding to the code. So if you look at the beginning, the function itself, it's tracing its own source code, so the debugger can know that this function execute. It's tracing a function call. Okay, this function has been called with these arguments. It's tracing binds, like the argument. A has been bound to the value A and everything like that. And then there is a lot of expression tracing. For example, if you want to see how this A is being traced, is this thing here. So it's basically trace and return the value of A and under the coordinate 3, 1, 1, 1. How does this coordinate works? It's basically, this is 0, 1, 2, and 3. Then this is 0, 1, etc. So 3, 1, 1, 1, it's basically 3, 1, 1, 1, since it's 0 based. So that's how it basically instrumented. It's not, I mean, not rocket science, just the same thing you normally do with print statements, but it's doing automatically and tracing. Okay, so yeah, if this is going to generate a bunch of traces, then there is the other part of FlowStorm, which is we need to index all those traces so we can build that those tools, for example, to the tree and function list and whatever. I'm not going super deep in this diagram, but it's basically, it's FlowStorm, it's building a tree. Every node of the tree is a function call, and every node it's a function called frame. So it's going to have the function namespace, function names, the argument it was called for, all the bindings that are inside that frame, and all the expression results inside that frame. And then we also have this other index, which is basically what we use to step forward and backward and jump in time, which is the trace position pointing to different parts of the tree. But yeah, I guess we can create a bunch of other indexes if we want to like quickly visualize other aspects of our execution. And that's it. Some known limitations of this. Super big forms can be fully instrumented, and this is because the Clojure compiler has a limit on how big forms it can accept. And if the form is already big, instrumentation is going to add a lot of extra code. So sometimes you go over that limit. In that case, FlowStorm automatically downgrades to light. So it tries to instrument it anyway, but now it's only going to trace function calls and function return for that specific form. The other thing it's FlowStorm just skip if we are trying to implement a function that contains a recur, but without a loop. And this is because we cannot wrap this thing in anything, because then it's not in tail position anymore. And if we don't wrap it, then we don't have the function return. So yeah. And kind of a similar situations, it's if we have like lazy sequence that are calling recursively and stuff like that. But probably some of these can be fixed. I'm not sure. And then it's Clojure script current limitations. So these are not like theoretical limitations. This is just, I mean, I didn't have time to implement. So for Clojure script, there's no browser. And no namespaces or bar instrumentation. So this stuff that we did from the browser, like instrument the entire namespace or whatever, it's not there yet, but can probably be implemented by connecting to a REPL, to a Clojure script REPL. And yeah. And some ideas for the future. Next thing I want to try is like improve, have a better value inspector, like what Rebel has and Reveal and Portal, because current value inspection, even if it has that thing that you can send it to the REPL and then you can send it to Portal, for example, but I would like to have a better value inspector there. Then I'm super interested in this. I haven't tried yet. I'm calling it execution derived types and documentation. And this is because now that FlowStorm can instrument any Clojure code base, I want to try to instrument an entire project, exercise the code base by, for example, running tests, and then sample absolutely every function call that's happening and return values and everything. And if we sample that, we can derive types and documentation, for example, like function calls examples and stuff like that, which I think could be pretty nice to have for projects. And then I want to also do try integrations with, for example, async profiler and Java object layout and all those tools that we already have, but I would really like to have them inside the same UI, so you don't have to remember how to run them or whatever. But yeah, those are my ideas for the future. So thank you very much for watching the presentation. Try it out. Contribute, open issues. There is a Slack channel there, FlowStorm, that you can go if you are interested in talking about debuggers in general, Clojure debugging or whatever. I'm pretty interested in that. Yeah, that's it.
Fantastic.